Good morning everyone. This is Dr. R. Lakshmi of St. Peter's Engineering College. So just previous to this class, I have been explaining you about the concept of the quadratic forms and canonical forms and how the quadratic forms can be reduced to canonical forms. Now in this class I am going to teach you the problems based on the conversion of quadratic forms to canonical form. As I told you in the previous session, the quadratic form can be converted into the canonical form in different ways, right? So using orthogonal transformation x equal to py, every quadratic form be transformable to the canonical form. There are two such other methods. Lagrange's reduction is also another important method, and one more diagonalization method is there for converting the quadratic form to canonical form. In this session, out of all the possible methods, I am going to explain the orthogonal transformation method, and we are going to reduce the given two quadratic forms to the corresponding canonical forms. Look at the first question. X square plus 3y square plus 3z square minus 2yz. This is a quadratic form, right? So by our process of getting into the canonical form, we have to first write the coefficient matrix of the quadratic form. As we all know, the matrix or the coefficient matrix of the quadratic form is A is equal to, how do we get this? From the square terms of the quadratic form, in the order of variables, we have to write the diagonal elements. It is 1, 3, 3. And to write the remaining elements of A, we depend on the product terms. Only one product term is there, minus 2yz. Because y is the second variable, z is the third variable. In the place of 2, 3 or 3, 2 means second row, third column or third row, second column. At these two places, we have to write half of the coefficient minus 2. It is minus 1 should be written. There are no other product terms. We have the remaining all the terms of A become 0. So this is how we determine the coefficient of the quadratic form. Now we have to find the eigenvalues and eigenvectors of this. To find the eigenvalues, we have to write the characteristic equation, which is det of A minus lambda equal to 0, which is given by det of, to write down this A minus lambda I, we have to subtract from the diagonals of A lambda values, right? Because in lambda I will be having non-zero elements only along the diagonal, which are lambdas. So writing the corresponding characteristic equation, inside the det symbol A minus lambda I we get, it is from the first row, it is 1, 0, 0 written as 1 minus lambda 0, 0. Second row is 0, 3 minus lambda minus 1. Third row is 0, minus 1, 3 minus lambda. When we expand the determinant, we get 1 minus lambda of 3 minus lambda into 3 minus lambda whole square. It is 9 plus lambda square minus 3 lambda minus 3 lambda. It is minus 6 lambda, right? Minus, we have minus 1 into minus 1 plus 1. And remaining two elements of the first row are 0. There are no other elements we get in the expansion. So we get equal to 0 on the right side. And this is 1 minus lambda into, this is lambda square minus 6 lambda plus 9 minus 1, it is plus 8 is equal to 0. When the two factors are multiplied, from the first factor we write first, lambda is equal to 1. When we factorize the quadratic factor here, we get here lambda minus 4 into lambda minus 2. So lambda square minus 4 lambda minus 2 lambda minus 6 lambda minus 4 into minus 2 plus 8 we get. So the factors of this quadratic factor are lambda minus 4 into lambda minus 2, which is equal to 0. So after this we get lambda is equal to 1 comma. When lambda minus 4 0 we have 4. When lambda minus 2 0 we have 2. Therefore the eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 4, lambda 3 is equal to 2 for the given matrix of the quadratic form. Now with these three eigenvalues we have to determine the corresponding eigenvectors that we do here. When lambda 1 is equal to 1, suppose that x1 is equal to the column xyz be the eigenvector, right? Be the eigenvector. From this lambda 1 and x1 using the matrix U of the quadratic form, now the homogeneous system can be written as from the first row, when we subtract 1 from the diagonal element, we have 1 minus 1, which gives us 0. So we have 0 into x plus 0 into y plus 0 into z equal to 0. From the second row, we have 0 into x, diagonal minus eigenvalue 1 should be taken, so 3 minus 1. We get 2 into y minus 1 into z, minus z equal to 0, 1 and 2. From the third row, we have 0x minus y plus 3 is a diagonal, so from this 1 has to be subtracted. So we get 3 minus 1, 2, z equal to 0. We have the first equation completely 0. Since 2y is equal to z and y equal to 2z, which is possible only when y is equal to z equal to 0, this we get from 2 and 3. So because from 2, 2y equal to z and from 3, y equal to 2z, the only chance we can have is both y and z are 0. But the three equations are not depending on the x variable. Therefore, we suppose that the other variable x is equal to an arbitrary constant k. Therefore, the first eigenvector x1 is equal to the column of variables x, y, z, where x is equal to k. Suppose we choose for k the value, simplest value 1. We got x equal to 1, y0, z0. This is the eigenvector corresponding to the first eigenvalue lambda 1 equal to 1. Now let us find the eigen. If the eigenvalue is equal to 4, what is the second eigenvector x2, which is the column x, y, z. Okay. So we are supposing x to be the eigenvector for eigenvalue 4. With this 4 and x2, using the matrix of the quadratic form, we have the corresponding homogeneous system is equal to, we have from the matrix A, the first row is 1, 0, 0, second row is 0, 3, minus 1, third row is 0, minus 1, 3. Okay, now corresponding to this eigenvalue 4 from the first row, we have 1 minus 4. It gives minus 3x plus 0y plus 0z. So we have minus 3x equal to 0. From the second row, it is 0, 3 minus 4. We have minus y, next is minus 1. So minus z equal to 0. From the last row, 0x, minus 1 ante minus y. Next 3 minus 4 means minus z equal to 0. First equation gives x equal to 0. Because the third and the second are the same equations, we have from the 2 or 3, it implies minus y equal to z or y is equal to minus z, which is nothing but y by 1 equal to z by minus 1, and therefore the second eigenvector corresponding to 4 is with x equal to 0, y is equal to 1, z equal to minus 1. Okay, now corresponding to the third eigenvalue lambda 3 is equal to 2, we have, let us suppose that x3 is equal to the column xyz be the eigenvector. Corresponding to this 2 of the eigenvalue 2 of the matrix A, from the first row we have the homogeneous equation 1 minus 2, we have minus x. Remaining coefficients are zeros, so we don't have the other values of y and z coefficients. Minus x is 0. From the second row we have 0x plus 3 minus 2, we have y minus z is equal to 0. From the third row we have 0x minus y plus 3 minus 2, we have plus z is equal to 0. First equation gives x 0, and second and third equations are the same equations again. Any one of them implies y equal to z, which is y equal to 1 and z equal to 1, and hence the third eigenvector will become x equal to 0, y is 1, z is 1. So first eigenvalue is 1 0 0 corresponding to 1, second is 0 1 minus 1 corresponding to 4, third is 0 1 1 corresponding to eigenvalue 2. It is clear that x1 do not depend on x2 x3. Similarly x2 do not depend on x1 x3. Similarly x3 do not depend on x1 x2, and therefore we say that the three eigenvectors are linearly independent. Also we can say that since x1 dot x2, which is x1 transpose x2, what do we get here? 1 0 0 row. It is x1 transpose, so 1 0 0 the row into x2, which is 0 1 minus 1. We get 1 into 0 plus 0 into 1 plus 0 into minus 1, 0, which implies that x1 comma x2 are orthogonal. They are orthogonal to each other. With the same reason, we have x2 dot x3 0 and x1 dot x3 0, which implies that the eigenvectors are pairwise orthogonal also. Now we form the normalized model matrix with the three linearly independent eigenvectors. With the normalized model matrix, the model matrix is obtained in this way. It is E1, the first normalized vector, next E2, next E3, where E1 is given by x1 by norm x1, E2 is given by x2 by norm x2, E3 is given by x3 by norm x3. Since x1 is equal to the vector 1 0 0, we have the norm of x1 is equal to root over 1 square plus 0 square plus 0 square, it is root 1 equal to 1. Since x2 is equal to the vector 0 1 minus 1, we have the norm of x2 is equal to root over 0 square plus 1 square plus minus 1 whole square, it is 2. So similarly for x3, which is 0 1 1, again the norm of x3 with the same reason, it is equal to root 2. With the norms dividing the vectors, elements of the vectors, we have the normalized model matrix is 1 0 0. From the second eigenvector x2, we have 0 1 by root 2 minus 1 by root 2. Similarly, the third normalized vector is 0 1 by root 2 1 by root 2. By the process of its construction, this P is orthogonal. This P is orthogonal. Since P is orthogonal, we can now form, we can get the orthogonal transformation x is equal to orthogonal transformation x is equal to Py, where x is equal to the column of variables of the quadratic form x, y, z from the given problem, and the matrix P is as we get here, and the matrix Y is the column of variables of the required canonical form. If the variables of the canonical form are taken as y1, y2, y3, this become the orthogonal transformation. Now, using this orthogonal transformation, let us reduce the quadratic form to the canonical form, right? The given quadratic form is x transpose Ax. It is x transpose Ax. When this x equal to Py is applied over that, we have Py the whole transpose into A into Py. On simplification, this is Py the whole transpose is y transpose P transpose into A into P. Multiplication of associative is satisfied in matrix multiplication, and in the middle this P transpose AP we get from the process of diagonalization of the matrix to be a diagonal matrix D, where the eigenvalues are the diagonal elements. So we get here y transpose, which is the row matrix y1, y2, y3 into the diagonal matrix whose diagonal elements are eigenvalues of the matrix A. It is 1 4 2, right, into the matrix Y, which is y1, y2, y3. When we multiply the three matrices, we get, it is the diagonal element 1 into y1 square plus the diagonal element 4 into y2 square plus the diagonal element 2 into y3 square. And this is what our required canonical form. Now with this canonical form, the rank of the quadratic form is, because in the quadratic form, the required number of terms are only 3, being a 3 by 3 matrix we get for the quadratic form. All the 3 terms are positive. We have 3 non-zero terms in the canonical form, so the rank is equal to 3. All the 3 terms are positive, so the index is also 3. After getting the index, we have the signature of the quadratic form is 2 into R minus S. It is 2 into 3, 6 minus 3 is equal to 3. And the nature of the quadratic form is, because all the possible 3 terms of the canonical forms are positive, the nature of the quadratic form is known to be positive semi-definite. Now similarly, let us solve the second problem shown here. Let us also reduce this quadratic form to the canonical form in the same method. Right? This is our problem now. Let us have the solution. So what is our first step? We have to find the matrix of the quadratic form. We have the matrix A of the quadratic form is equal to, from the square terms coefficients 2, 2, 2 taken along the diagonal, from the product minus 2 x1 x2. Here for the quadratic form, capital X is equal to the column x1 x2 x3. From the product term minus 2 x1 x2, we have minus 2 is made into half. We get in the first row second column, second row first column, the two halves. Similarly, from minus 2 x2 x3, second row third column, second row third column, third row first column, again minus 2 by 2, minus 1 taken at both the places. Similarly, minus 2 x1 x3 gives minus 1 at the respective places. Now the characteristic equation of this is, det of A minus lambda I is equal to 0, which gives us the det of, from the first row 2 minus lambda minus 1 minus 1, from the second row minus 1 2 minus lambda minus 1, from the third row minus 1 minus 1 2 minus lambda is equal to 0. On expanding the determinant, right, we get 2 minus lambda into 2 minus lambda whole square. It is a 4 plus lambda square minus 2 lambda minus 2 lambda minus 4 lambda minus 1 into minus, it is 1. Next element is minus 1 in the first row. Its cofactor is negative, so minus of minus 1. It is plus 1 into minus 1 of 2 minus lambda. Minus 2 plus lambda minus 1 into minus 1, it is 1. Next element in the first row is minus 1. Its cofactor is positive. So minus 1 of minus 1 into minus 1, 1. Minus of minus become plus 2 minus lambda is equal to 0. So when we simplify this expression, we have 2 minus lambda into lambda square minus 4 lambda plus 3. And here minus 2 minus 1. It is minus 3 plus lambda. From here we have 3 minus lambda into minus. So it is minus 3 plus lambda is equal to 0. And we get here minus lambda cube after simplification plus the trace of the matrix is 3 2s are 6. So we have 6 lambda square. And the coefficient of lambda is, we have 2 into minus 4 lambda, we have minus 8 lambda, minus lambda into 3, we have minus 3. From here we have 2 lambda, so it becomes plus 2. So when it is minus 8 minus 3, we have minus 11 plus 2, we have minus 9. It is minus 9 lambda. And the constant term we have is 3 into 2, 6. Again here minus 3 we have minus 6. Right? We have the coefficient is equal to 6 minus 6 is equal to 0. So no constant term here, we have 0. And this can be written lambda cube minus 6 lambda square plus 9 lambda equal to 0, or lambda into lambda square minus 6 lambda plus 9 is equal to 0, which gives us lambda into lambda minus 3 the whole square equal to 0. Thereby we get lambda equal to 0, 3, 3. And hence the 3 eigenvalues are lambda 1 0, lambda 2 equal to 3, lambda 3 is equal to 3. So what are the eigenvalues of the second problem? They are lambda 1 equal to 0, lambda 2 equal to 0, lambda 3 is equal to 3. Now for these three eigenvalues, let us determine the corresponding eigenvectors. Let us determine the corresponding eigenvectors. Eigenvectors. Suppose we choose the first eigenvalue lambda 1 equal to 0. Suppose x1 equal to xyz be the eigenvector. Then what happens? The corresponding homogeneous system. We have the matrix A is equal to diagonals 2 to the remaining all the elements are minus 1. So from this we can very easily find out the homogeneous system. When lambda 1 is 0, we have from the diagonal 2 minus 0, 2 minus 0, 2 minus 0, the homogeneous system remains the same. We can write directly from the each row. It is 2x minus y minus z 0, minus x plus 2y minus z equal to 0, minus x minus y plus 2z equal to 0. All the equations are different. So when we consider the first equations 1 and 2, when we apply the cross multiplication method, we write the variables first. Then starting from the coefficient of y, we write minus 1, 2, minus 1. From the second equation, 2, minus 1, 2. Thereby we get x by 1 minus of minus 1 plus 2, 3. Next it is y by 1 minus of minus again 3. Next is z by, it is a 4 minus 1 again 3. Cancel 3. So we have x by 1, y by 1, z by 1. Thereby giving the first eigenvector is 1, 1, 1. Are you following? And is the finding of first eigenvector 1, 1, 1 is clear to all of you? I hope you all are clear with the process we are doing. Now corresponding to lambda 1, 0, the eigenvector is 1, 1, 1. Please remember. Now corresponding to the second eigenvalue, lambda 2 is equal to 3. Suppose that x2 equal to xyz be the eigenvector. So I am writing here for lambda 1, 0, the eigenvector is 1, 1, 1. Right? Next we write here for lambda 2 is equal to 3 and 3. What are the corresponding other eigenvectors? Now corresponding to this x2, which is for lambda 2 equal to 3, the corresponding homogeneous system, we write from here A matrix row wise, subtracting 3 from each of the diagonal. Row wise when we write, we can have the equations. So 2 minus 3 gives us minus x minus y minus z equal to 0. From the second row, minus x minus y minus z 0. From the third row also we get the same equation. Since all the three equations are the same, we consider only one. Suppose we consider x plus y plus z equal to 0 after cancelling negative sign with the right hand side 0. Because there is only one equation in the homogeneous system with three variables. Unless and otherwise, two of the variables are given some arbitrary value, we cannot get the third variable. So our option is here, choosing an arbitrary value for two of the variables and depending on them to find out the other variable. Now suppose that y is equal to k1 and z is equal to k2. Therefore we get x is equal to minus k1 minus k2 minus of k1 plus k2. And with this the second eigenvector is minus k1 minus k2 k1 k2. And this can be written as k1 into minus 1 1 0 plus k2 into minus 1 0 1. Suppose we choose the value of k1 equal to 1 and k2 is equal to 0. We are going to get the second eigenvector minus 1 1 0. The second eigenvector is minus 1 1 0. Now corresponding to the third eigenvalue. Okay. I am showing here. Corresponding to the third eigenvalue, when we repeat this entire process, we need only to change the k1, k2 values here. Here for the choice, let us choose k1 to be 0 and k2 equal to 1. So that the third eigenvector we get minus 1, 0, 1. That is minus 1, 0, 1. Minus 1, 0, 1. Now let us see whether the three eigenvectors are linearly independent and pairwise orthogonal. It can be clearly observed that the three eigenvectors are linearly independent. Now let us see whether they are orthogonal or not. When we multiply the first two, transpose of the first one into the second in order to find the inner product. It is -1 + 1 0. Okay, first two are orthogonal. When we multiply the second vector with the third vector, taking the transpose of any one of them, we have 1 + 0 + 0. The last two vectors fail to satisfy the orthogonality. So we have to change either the vector x3 or the vector x2. So for the instance in this problem, we are going to keep x1 and x2 as it is, and we are going to change our x3 as, we are going to take it as ABC. And we require now this ABC in such a way that the column ABC is orthogonal to both x1 and x2. And that means this x3 dot x1 and x3 dot x2 should be 0. Now using that fact, let us determine what are the values of ABC. Okay. Because x3 vector must be orthogonal to x1 and x2. So we need x1 dot x3 0. Also x2 dot x3 is equal to 0. Right? Our x1 is 1 1 1. x3 is ABC. Multiplying the two, we have a plus b plus c equal to 0. Next, we must have x2 dot x3 0. Our x2 is -1 1 0. x3 is ABC. Multiplying them, we have -1 into a plus 1 into b plus 0 into c. We have -a plus b is equal to 0. The two homogeneous equations. Again, because the equations are different, we can apply the cross multiplication for getting their values. Or otherwise, we can also apply the simple process. From the second, we write a is equal to b. When we have a equal to b, from this equation we can write, because b is equal to a or a equal to b, we can write 2 into a plus c equal to 0, which gives us 2 into a is equal to -c, or a is equal to -c by 2. From the two equations we can write a is equal to b is equal to c by -2. And therefore we get the column ABC is equal to a is 1, b is 1 and c is equal to -2. And this we take as the new eigenvector x3 instead of the previous eigenvector. It is +1 +1 -2. Now clearly it can be observed that x2 dot x3 is 0, x1 dot x3 is 0, along with x2, along with x1 dot x3, x2 dot x3, right, and x1 dot x3. Pairwise they are orthogonal now. Because the eigenvectors are independent and pairwise orthogonal, now we can form the normalized model matrix E1, E2, E3. Where E1 is the normalized x1, it is 1 by root 3, 1 by root 3, 1 by root 3, where the root 3 is the norm of the vector x1. Similarly, from the second eigenvector -1, 1, 0, since the norm is root 2, we have -1 by root 2, 1 by root 2, 0. Since the norm of the third eigenvector is root over 1 plus 1 square plus 1 square plus -2 whole square, we get root 6. We get E3 equal to column 1 by root 6, 1 by root 6 minus 2 by root 6. By the process of the construction of this P, this is always orthogonal. Because this P is always orthogonal, using this P, we can have the orthogonal transformation x is equal to P1. And using this orthogonal transformation, every quadratic form which is x transpose Ax always reduces to, when we apply x equal to Py over x transpose Ax, it always reduces to y transpose dy, where y is equal to the column of variables of the coefficients as the diagonal elements of D. And the elements of this D are the eigenvalues of the matrix of quadratic form, which are 0, 3, 3. So we write here 0 into y1 square plus 3 into y2 square plus 3 into y3 square. we have the three terms of the canonical form, wherein one of the term is 0, the other two terms are positive. With this knowledge of canonical form, now the rank is equal to, as there are two non-zero terms out of the three. Because the quadratic form has three variables, we must have three zero or non-zero terms in the canonical form. There are only two non-zero terms in the canonical form, the rank is 2. Similarly, the index. There are two positive terms. Because 0 is neither positive nor negative, the positive terms are only 2, so index is also 2. The signature of the quadratic form. It is 2 into r minus s. It is 2 into 2, 4 minus 2 is equal to 2. And the nature of the quadratic form is, out of the three possible terms of the canonical form, we have one zero term and two positive terms. Therefore, we say that the nature of the quadratic form is positive semi-definite. It is positive semi-definite. I hope you all, from the two examples I have explained you all understood the method of converting the quadratic form to canonical form using the orthogonal transformation x is equal to py. Please do practice more sums in this, because this is the only method included in your syllabus for you. So practice more and more problems so that you get more clarity over the problem doing. Thank you all.